Hello, and we're back with Chapter 11, Infinite Sequences and Series, Section 11.5 on alternating series. So what is an alternating series? An alternating series is one where the terms alternate their positive or negative sign. So you're always going to see, in this case, a minus 1 to the n minus 1, or a minus 1 to the n, or minus 1 to the n plus 1, followed by an expression in n, where the b sub n's here in this setup are positive terms. But you'll see if I were to write out the terms of this sequence, and in this case when n here is equal to 1, and 1 minus 1 is 0, so our very first term would be positive. And just to be clear from all of the other series tests, remember when we're looking at an infinite sum, the entire expression is a sub n. So the entire expression would be a sub n. And in other words, a sub n would be minus 1 to the n minus 1 times b sub n. Good. But we just want to have that factor of minus 1 to the nth power to indicate that the terms of your series are changing in sign, and it has to change plus minus plus minus plus minus, or minus plus minus plus minus plus. You can't just have them have no pattern of positive or negative signs. So what is the alternating series test? The alternating series test is if you can demonstrate the two criteria below here, then you can determine that the series is convergent. So what are the two criteria? Well, first, your b sub n plus 1 has to be less than or equal to b sub n for all n. In other words, show that the b sub n are decreasing. Right. You can take some concrete examples. If n is equal to 2, you'd have b3 is less than or equal to b2. If n is equal to 4, then we would have b5 is less than or equal to b4, etc., etc. Right? So we have that the b sub n's are actually decreasing. But not only that, we must show that the limit of the b sub n terms is actually going to 0. So the idea behind this series, so that we can convince ourselves that we do have a convergent series, is mostly geometric. So if I were to graph this scenario on the number line, and let's just say, for instance, that the very first term, b sub n, is positive. So if I were to think of the sequence of partial sums, remember below that S sub n is a1 plus a2 plus a3 plus dot 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 plus a sub n. And remember, a series is convergent if its sequence of partial sums converges. And then the sum of that S sub n would actually be the sum of the series, or the limit would be the sum of the series. If you wanted to connect it with the b sub n's, this would be b sub 1 minus b sub 2 plus b sub 3 minus b sub 4 plus dot 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 plus b sub n, right? They would plus minus. Remember that your b sub n's are positive terms, but you're subtracting and adding them. So if I were to start with a sequence of partial sums, remember whenever I add a number on the number line, I move to the right. And whenever I subtract something on the number line, I would move to the left. So if I just started from 0 here, and let's say, for instance, I am adding plus b sub 1, right, just to assume that b sub 1 is, or the very first term here is positive, and the b sub 1 is a positive term. So in this case, I would have b sub 1, but we know that that's equal to s sub 1. And if I were to take the s sub 2, then it would be b sub 1 minus b sub 2, right? As an example, s2 here would be b sub 1 minus b sub 2. And s sub 3 here would be b sub 1 minus b sub 2 plus b sub 3. Good. And whenever we subtract something on the number line, we're going to move to the left. So I would go forward plus b sub 1, but then I would be going backwards to b sub 2. But remember that b sub 2 does not go all the way back so far because your b sub 2 is smaller than b sub 1. So this would be my minus b sub 2, and this value here would then be s sub 2. And if I were to create the next term in my sequence, what would its value be? If I'm going to find s sub 3, I'm going to add b sub 3 to it. And in this case, I'm adding, but I'm not going quite all the way back because b sub 3 is less than or equal to b sub 2 because it's a decreasing sequence of terms. So this value here is going to be s sub 3. And if I keep going, it's very necessary. So I'm here relying upon the fact that the b sub i's are decreasing. I'm also needing to rely upon the fact that b sub n's have to actually have a limit of 0 so that we would spiral back and forth, right? Because I would just keep going back, not going back so far, and this would be my s sub 4. And then I would be going back again, but not so far, and that would be my s sub 5. And eventually I would be cycling down because the b sub n's are going to 0. I would eventually end up with somewhere in the middle is going to be s. Good. Notice here that if the b sub n plus 1 less than or equal to the b sub n, and the limit as n goes to infinity of b sub n equals 0, then we would have the minus 1 to the n minus 1 of b sub n from n equal 1 to infinity converges, because we'll see that the limit of the s sub n's is going to equal s, right? Because the s sub 2, it will be an upper, your sum is going to be an upper bound of the subsequence of partial sums that are even, and it's going to be a lower bound for the odd ones. So you can take a look at this number line here, the sum of the series. Your odd numbered partial sums are always going to be above your sum, and the even ones are going to be below. But because the b sub n's are going to 0, let's say if they didn't go to 0. If they didn't go to 0, then if they went to another number, then eventually at infinity, you'd be oscillating back and forth an equal number, equal to that limit. You'd be adding it, then subtracting it, adding it, then subtracting it, and you would not be spiraling into a sum. So you definitely need to have the b sub n's go to 0. So that is the motivation, but both of those criteria are met for you to make a conclusion. So let's actually use that test on a couple of these. And when do you want to consider the alternating series test? When you do recognize that you've got a factor of minus 1 to the n, or minus 1 to the n minus 1, or minus 1 to the n plus 1 in your a sub n expression. So I see that here. Let's look at the alternating harmonic series. We can see that this is equal to minus 1 to the n minus 1 times 1 over n. So this portion here, I have that b sub n is equal to 1 over n. So criteria 1 is we want to show that the b sub n are decreasing. And if you remember back to the integral test, we needed to demonstrate that if the a sub n's were decreasing and they were positive terms in order to use the integral test, reminding ourselves, how do we show that something is decreasing? You have two options. You can either show directly by showing that b sub n plus 1 is less than or equal to b sub n for all n, or B, for f sub n equal to b sub n, show that f prime of n is negative for all n, right? So either way, in this case, because b sub n is simple, we just have the expression 1 over n, then it's easy to show directly. So is it true that 1 over n plus 1, is that less than or equal to 1 over n for all n? That is certainly the case. If I cross multiply, we want to say n times 1, is that less than 1 times n plus 1? And that is certainly true. So it is decreasing. And then part 2, we want to show that the limit as n goes to infinity of the b sub n is equal to 0. We have that the limit as n goes to infinity of 1 over n is going to go to 1 over infinity, which does equal 0. So our conclusion here is that the sum of minus 1 to the n minus 1 over n from n equal 1 to infinity converges by alternating series test. Good. All right. So again here, this one is also very similar. We want to see that the entire expression outside of the minus 1 to the n is going to be your b sub n. Good. And we do have that this is an alternating series because of the factor of minus 1 to the n. So part 1 is showed b sub n are decreasing. So I'm going to again show directly, and I'm going to say does 1 over the square root of n plus 1 squared plus 1, is that less than or equal to the 1 over the square root of n squared plus 1, right? This is my b sub n plus 1 on this side. Good. And if I cross multiply, we're asking ourselves, does the square root of n squared plus 1, is that less than or equal to the square root of n plus 1 squared plus 1? Is it true that n squared plus 1, is that less than or equal to n plus 1 squared plus 1? And we can certainly say that yes, that is true. You don't have to go all the way but down to n if you don't want to. This is obviously the case that this is true for all n. Part 2 is how do we show that the limit as n goes to infinity of your b sub n is equal to 0? We have the limit as n goes to infinity of 1 over the square root of n squared plus 1. That is going to go to 1 over infinity squared plus 1 square root, which is going to 1 over the square root of infinity, which is infinity, and that is going to 0. So conclusion, my series of minus 1 to the n times 1 over the square root of n squared plus 1 converges by the alternating series test. Okay, so let's look at this one. What is our b sub n? Our b sub n is n over n plus 1. And I can see here that we can try to demonstrate part 1. We can say show decreasing. And I'm going to show that for f of n equal to n over n plus 1, show it is decreasing. Or show that it is negative. Let's see if it is. So if I take my derivative here, that's going to be the derivative of the top times the bottom minus the top times the derivative of the bottom, all over the bottom squared. And this one is going to equal n plus 1 minus n is just going to be 1 over n plus 1 squared, and that's actually equal to a positive over a positive. And so we have that it's bigger than 0, so this is not decreasing, it's actually increasing. So that's a problem. But also part 2, the limit as n goes to infinity of my b sub n is going to equal the limit as n goes to infinity over n of n over n plus 1. And you can either factor out the highest power, or you can do L'Hopital's rule, because it goes to infinity over infinity. And that's going to equal n as n goes, limit as n goes to infinity of 1 over 1, which is equal to 1. So the limit of the b sub n's does not equal 0. And because of that, we see this implies that a sub n equal to minus 1 to the n of b sub n, or n minus 1 of b sub n, is its limit is going to go to plus or minus 1, which does not equal 0. So really, by the divergence theorem, since the limit of your a sub n does not equal 0 as n goes to infinity, your series diverges, right? And since our series is our alternating series, we're done. It diverges. Good. I hope that is clear. This one, finally, as another, we'll probably do in office hours, or I might write that up later. But you can see the point. Try to show that that is a decreasing by either showing it directly, or in this case, I might show that the derivative of that is negative. All right. So another thing about alternating series is that if you have a convergent alternating series, you can estimate its total sum with a partial sum and know what the error in your estimate will be. So remember that if your series is equal to a sum, then our sum S is going to equal a partial sum plus a remainder, right? And so we do know that our S sub n is going to be your A1 plus A2 plus dot 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 plus A sub n. But in this case, because we have alternating series, we have B sub 1 minus B sub 2 plus B sub 3 minus B sub 4 plus dot 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 plus B sub n. Good. And our R sub n here is going to be an plus 1 plus an plus 2. It's the tail end of your series. Good. And that tail end might be that b minus b sub n plus 1 plus b sub n plus 2 minus b sub n plus 3 plus, remember when you introduce the b sub n's, if you're going to look at the sequence of partial sums, a sub n's, you're still adding the a sub n's, but the b sub n's are positive, but you're switching the sign with the minus 1 to the n. But if you return back to, so look at this estimate here. It says if you've got a convergent alternating series, that satisfies that you've got decreasing b sub n's and you've got the limit as the b sub n goes to 0, so we do have that convergent series, then your r sub n, which is the error in your estimate. So remember, your s sub n would be the estimate of the sum s. So if you wanted to add the first couple of terms, you might get really close to the sum of your series, and your r sub n is going to be the error in approximating the series sum with S sub n. Good. So when we have those two facts, we go back to that geometric interpretation, And you do see that your even sums are smaller than your odd sums, back to the sequence of partial sums here. But you'll notice that, your S sub 2 is smaller than your S sub 3. Your S sub 4 is smaller than your S sub 5, because the S sub 2s and S sub 4s are smaller than the sum, but the S sub 3s and the S sub 5s are bigger than the sum. But you can see those subsequent sums. So the idea behind this and demonstrating this proof is that we do have S minus your partial sum, which is equal to the R sub n. That's going to be less than or equal to, if I just go to the very next one, remember that's going to be above it, minus the S sub n, just assuming that if n's even. And you could make a similar argument with subtraction inside the absolute value. But in this case, your S sub n plus 1 minus your S sub n is actually going to equal the absolute value of B sub n plus 1, right? And that, because the B sub n's are already positive, the absolute value is just going to be B sub n plus 1. So it's a pretty nice application that however many terms that you add up of your convergent alternating series, you're never going to be off from the real sum by anything more than the very next term. And that's pretty cool. So in the interest of saving time here, I have gone ahead and done some of these examples to give you an idea of how to solve problems like this. So look at example 2 here. We've got, consider the alternating harmonic series, the sum from n equal 1 to infinity of minus 1 to the n minus 1 over n. And the first problem it asks, find the 20th partial sum. So we're here finding S sub 20. So what would S sub 20 be if I'm going n equal to 1, then minus 1 to the 1 minus 1 is minus 1 to the 0, and that would be over 1. So we do know that the very first term is going to be positive, which means the second one's going to be negative, and the third one's going to be positive. But we're going to go up by 1 in the denominator because we've got 1 over n. So our S sub 20 is 1 over 1 minus 1 half plus 1 third minus 1 fourth, and all the way up to minus 1 20th. And if I convert these fractions into decimals and then find that sum, I end up with S sub 20 being 0.669. And then it asks, estimates the order of error attained from this partial sum. So it's asking me, how much am I off by if I'm estimating the total sum of this convergent series? And remember, this is the alternating harmonic series, and we did demonstrate that that does converge. Well, I'm only going to be off by the very next term, and the very next term would be B sub 21. And B sub 21 is 1 over 21 because B sub n is 1 over n. And 1 divided by 21 is 0.048. So that's 48 thousandths. That's how much we're off by, and that's not that much. The next question asks, how many terms in the series are needed to estimate the sum to an order of error no more than 10 to the negative 3? So we want our error to be less than 10 to the negative 3 because we don't want the error to be any more than that. So let's make it less than that. And that will tell me how do I solve for n. So our B sub n is 1 over n, so B sub n plus 1 is going to be 1 over n plus 1. And I don't want that to be less, or I don't want that to be any more than 10 to the negative 3, which is 0.001. And just getting rid of the decimals, I can multiply on both sides by 1,000, so I end up with 1,000 over n plus 1 less than or equal to 1. If I cross multiply, then I would get 1,000 less than or equal to n plus 1. So that tells me if I solve for n, if I choose n to be bigger than 999, then my error in estimating the sum is going to be no greater than 10 to the negative 3. So in other words, S sub 999 is going to be approximately equal to S, and my R sub n is going to be less than or equal to 0.001. And so that's what my estimate should be. Again, with this example 3, we've got our series is minus 1 to the n over n times 10 to the n, and it says estimate that sum correct to 5 decimal places. So I want to figure out how many do I need, and I'm going to, again, let my R sub n be less than or equal to B sub n plus 1, and I don't want that to be more than 10 to the negative 5, and that's going to be 0.00001. So I did a little bit of cheating in the sense just to make it easier. It is true that if we have the same numerator in fractions, the bigger the denominator is going to be the smaller number. So 1 over n times 10 to the n is certainly less than or equal to 1 over 10 to the n because n is always bigger than 1. So I got rid of that factor of n there. And then I want that to be less than 0.0001. So if I if I multiply by 100,000 on both sides, I get rid of the decimals. And if I cross multiply, I get 100,000 less than or equal to 1 times 10 to the n, which is 10 to the n. And then I break down, in this instance here, 100,000 is 10 to the 5th. And so now I can equate the exponents. And I know that I want my n to be bigger than or equal to 5. So just to be on the safe side, I'm going to find my estimate to be 5 plus 1, right? I'm going to say this is going to be my estimate is S sub 6. And my S sub 6 is the sum of the first 6 terms. And when we begin with n equal to 1, we do start with the negative because we're starting with minus 1 to the n. And I write out the first 6 terms, and then I add them together, and I get negative 0.0953102. And I'm pretty certain that my estimate is off by no more than 0.00001, and that's a pretty darn good estimate. All right, so that does it for alternating series. Remember, you can only use the alternating series test if you actually have an alternating series. Do not choose it if it's not. That concludes it. Thank you very much.